The theory of the harmonicity of the field of light is an axiomatic theory which chooses as its geometrical space the projective space. Space, the fundamental distinction, the choice of geometrical space. My late professor at the National Technical University of Athens, Panagiotis Raftopoulos, expressed with extraordinary clarity a fundamental distinction between the perceptible space and the geometrical space, a distinction stemming from the Platonic boundary separating the world of the senses from the world of the ideas. The geometrical space constitutes a peculiar mental creation, completely different perceptible space, the elements of which we can access through the corresponding elements of the perceptible space via an abstract, purely intellectual process. As the only criterion of any geometry's truth is its logical consistency, this distinction allows us the opportunity to freely select the geometrical space in which to describe the physical events that are observed and measured in the perceptible space. Thus, this theory selects as its geometrical space the projective one, and as its geometry, the projective geometry established by Jean-Victor Poncelet. The axioms of projective geometry introduce automatically to the projective space the elements at infinity, which are considered totally equivalent to those not at infinity, and consequently undistinguishable. As a direct result of this introduction and equivalence, the projective straight line is a closed line through its point at infinity.
Oh.
Time. Definitions. 1. The definition of synchronized clocks given by Albert Einstein. Two relatively motionless distant clocks located at points A and B are by definition synchronous if equation 1 is valid, where TA is the indication of the clock at A when a ray of light leaves A to act B, TB the indication of the clock at B when the ray arrives there and is reflected backwards, and TA prime the indication of the clock at A when the ray returns there. 2. The definition of the measurement of the speed of light given again by Albert Einstein. This is given by equation 2, where only one clock is used and the travel of light is aller-retour. 3. The definition of the linear array of synchronized clocks, classical. Let's imagine in the Euclidean geometrical space a series of clocks along a graduated straight line at random positions, 1, 2, etc., all synchronized according to Einstein's definition. Let's call this arrangement a linear array of synchronized clocks, classical, figure 1. 4. The definition of the average speed of a moving material point, given by classical mechanics. This is given by equation 3, where Ti are measured by the last when the moving material point passed by the two corresponding points M and F plus 1.
This was
The philosophy of the theory. The science of physics, contrary to mathematical science, is basically empirical, practiced by human beings who being of a material nature, are restricted by their locality. We adhere to the philosophical thought of Weizsäcker and Heisenberg, as it is presented by the latter in his well-known book Physics and Philosophy, and can be summarized in the following statement by the former. Nature is earlier than man, but man is earlier than the natural science. We therefore believe that every natural science ought definitely not to ignore the existence of the observer, who observes and measures the events. of course, the observer concept is rather elastic and aims to refer even to the instrument through which the registration and measurement of events take place. The first fundamental hypothesis of the theory is as below. Matter interactions occur in the geometrical space at a speed that is essentially constant and independent of the relative speed of the interactive elements of matter. More specifically, matter interactions conducted through light occur in geometrical space at a speed essentially constant in magnitude, independent of the relative speed of interactive elements of matter, and equal to the speed of light which I measure in my perceptible space at the place where I am located. How do I measure the speed of light? By applying Einstein's equation to...
Are we on the correct slide?
Excuse me?
Yeah, it's okay.
It's okay.
Yeah, that's fine.
Kinematics of the material point. Let's consider figure 2. Yeah. An observer at the random position O outside the calibrated straight line E, furnished with last, on which the observed material point moves with a constant speed v less than c, measured by last. The observer is equipped with a clock, henceforth called the local clock, which is synchronized, according to Einstein's definition, with any one of the last clocks. The observer measures the speed of light with the local clock, according to Einstein's definition, and finds it in the vacuum to be c, a finite number. Now, the material point is located at position A, in the geometrical space, figure 2. However, in the observer's perceptive space, it is not located at A, but rather at the previous position A prime, such as that. In the time it took the material point to travel from A prime to A, light traveled from A prime to O. Thus we have equation 4. Let's call position A, where the material point is now located, simply the position. On the other hand, the position A prime, where the observer sees, measures it, and registers it now, I call conjugate position. This position has been called the retarded position by Richard Feynman. Thus, we conclude that in reality, the objects of study of physics by humans and not by omnipresent spirits are the moving bodies positions, are not the moving bodies positions themselves, but rather their conjugates. Our observer sees and measures the objects of his study, always at their various conjugate positions. This conclusion, evocative of the shadows in the cave paradigm in Plato's 7th book of his Republic, carries critical implications for the whole of modern physics. It is easy to prove via equation 5 that for a given speed v and a given direction of movement, a one-to-one correspondence exists between the conjugate position and the position in the Euclidean space. Figure 3 shows that for the given conjugate position A prime, the corresponding position for the direction of movement shown in the figure is A, and A1 is the corresponding position for the same speed and for the opposite direction of movement. These two positions are symmetrical with regards to the conjugate. Now position A is given, as well as the direction of movement, and the measure of speed v measured by Lasker. We are asked to locate conjugate position A prime, figure 4. From the well-known bisector theorem, we get equation 6, through which we find the points M and H. With the segment MH as diameter, we draw the Apollonian circumference which crosses line E at points A prime and A prime, which are the conjugate positions for the two directions of movement in the Euclidean space. Here, we have lost the symmetry. We have, however, discovered something else. We have discovered harmony. This is because the 4 points H, M, A, O constitute a harmonic tetra. we observe that the double ratio with signs given by the red equation equals -1, which constitutes the necessary and sufficient condition for a harmonic tetrad. Let's now consider the three lines parallel to line E, passing through points H and O. This band of lines, together with line E, constitute a harmonic tetrad independent of position A. From this harmonic band, we find the conjugate positions via the Apollonian circumference. Let now the material point be at the foot of the perpendicular P drawn from O to line E. The observer now sees it at its conjugate position P'. Thus we have equation 7. Let now the material point be found at such a position K, so the observer sees it at P, meaning that P is the conjugate of K. So we have equation 8. In this case, light has traveled its minimal route. Thus, when the material point is found at P, the observer sees it and measures it at P'. And when the material point is found at K, the observer sees it and measures it at P. In other words, when the material point travels the interval Pk, the observer sees it and measures it traveling the interval P'. It would be interesting to find the relationship between these two intervals. This is given by equation 9, and it is equal with the famous Lorentz contraction factor of special relativity theory. We see that this contraction is not real, and it happens because the speed of light is finite, so the information arrives delayed to the observer. With two other articles published in Physics Essays Journal, we have also shown that the relativistic phenomena, as the famous time dilation, are consequences of Plato's subtlety. Kinematics of the material point moving with superluminal speed measured by Lasker. During the last international symposium honoring Jean-Pierre Vigier, which took place in London, we had shown that the relationship V less than C is not a conclusion of the Lorentz transformation, but rather a hidden precondition of each analytical production. In other words, the Lorentz transformation can only be valid for V less than C. Consequently, a definite rigid law of physics forbidding matter to travel with superluminal speed in vacuum does not exist. We examine the case where the material point moves away from the foot of the perpendicular with a speed V bigger than C, and now is located at position A. What is the location of its conjugate positions? That is, where is it now seen by the observer? The answer is provided by the Apollonian circumference, figure 6. So, when the material point was at A2', it sent a signal to O. And when it was at A', it sent a second signal to O. These two signals, according to equation 10, arrive simultaneously at O now, when the material point is at position A. Thus, the mysteries X, as they have been characterized by Roger Perot, with the famous Strandinger's cut dominating, are not mysteries. They are simply the co-perception of conjugate positions, the co-perception of shadows, according to Plato. This introduction of the projective space allows us to extend the same approach in all cases dealing with both subluminal and superluminal speeds, as the projective straight line is a closed line, and thus all the conjugate positions of the moving material point are located in its past, although in some figures they appear to be in the future, as in the following. Kinematics of the material point in the projective space. Let's consider figure 7. A material point A approaching the foot of the perpendicular P, moving with superluminal speed measured by laser. We are seeking its conjugates. We can locate those, as before, via the Apollonian circumference. The impression is given that the past conjugate positions precede the present position. This is not true, as we are working in the projective space, and thus the projective straight line is a closed line. I note that we don't know the history of the material point's movement, which means that this is not the first time that it is running across the projective straight line E. Hence, the two conjugate positions A' and A2' are behind position A. We observe figure 8, thus, that as point A approaches the perpendicular foot, the Apollonian circumference that yields the solutions is rising relative to straight line E, so we can imagine that there are positions of A such that the corresponding Apollonian circumference will not have any real intersection points with straight line E, thus completely losing the conjugate. The problem seems to be severe because we will be involved in the adventure of discovering a space void of any field. I note that our first hypothesis refers to all the interactions of matter. Finding the boundary Apollonian circumference and boundary position A0, figure 9.
These are going on
Obviously,
YouTube, Dan.
the boundary Apollonian circumference is tangential to straight line E. We assume, therefore, that it has been drawn and it is tangential to straight line E at A0 prime, which is identical to A0 to prime. After some simple geometrical thoughts, we conclude that the boundary position A0 is found if we open an angle omega with the perpendicular, which has as cosine C over V, cosine. So, when the moving material point passes boundary position A0, the Apollonian circumference has no intersection with line E, and the conjugate positions disappear. The segment of straight line E defined by A0, P, and the symmetrical of A0 in reference to P is space where the gravitational and any other interaction with O does not exist. Moreover, the particle traveling this interval cannot be seen by the observer, this observer. The above statement does not mean that in this interval there are no conjugate positions at all, meaning that this interval appears void. No, it simply means that the positions within the above interval have no conjugates. This is the space of dark matter. The space of dark matter has the same construction law with the space of the Cherenkov radiation. The semi-angles of the two cones have the same cosine, C over V. The entanglement, fundamental theorems. If we choose as geometrical space the projective one, then the two conjugate positions of the moving material point become superposed at the observer's perceptible space, the measurement of which produces the entanglement. It is extremely interesting to study certain fundamental relationships of this superposition. One, for subluminal speeds. Let's assume that we are given the two conjugate positions A' and A2' and the speed v of the material point where v less than c measured by laser. We are seeking the geometrical locus of all observation positions O from which the moving material point would appear simultaneously at the two given conjugate positions A' and A2', which have a distance of 2 gamma. Suppose A is the position. This position and the point at infinity of the projective line separate the conjugate pair. After some simple geometrical considerations, we conclude the equation 19, where 2 gamma is the distance A prime, A2 prime, and B equals V over C. Therefore, as the sum of the distances of the observation positions from the 2 given points, A prime and A2 prime, remains constant, it follows that the position of observation O registers on the plane an ellipse having as focus points A prime and A2 prime. If we symbolize the major semi-axis with alpha and the minor one with beta, we have alpha squared equals beta squared plus gamma squared, the eccentricity epsilon equals V over C. Based on the above, we formulate the first fundamental theorem. The geometrical locus of the observation position from which a material point moving on the projective straight line E at subtubular speed V measured by Lask appears to be simultaneously at the 2 given points A prime and A2 prime, is on the plane an ellipse which has A prime and A2 prime as focus points and eccentricity V over C. As both the focus points and the eccentricity are known, the ellipse is fully defined. Also, as the assumed plane is random, it follows, first corollary, this geometrical locus in 3D space is the ellipsoid surface created by the rotation of the aforementioned ellipse around its focal axis, ellipsoid of revolution. As we see from equation 23, follows the second corollary. The minor axis of the ellipse equals its major axis contracted by the Lorentz contraction factor of special relativity theory. The above analysis produces a number of other interesting corollaries described in the book, which presents the theory of the harmonicity of the field of light. Excuse me. Yes. 2. For superluminal speed. Let's assume that we are given the 2 conjugate positions A prime and A2 prime and the speed V of the material point where V bigger than C measured by Lask. We are seeking the geometrical locus of all observation positions O from which the moving material point would appear simultaneously at the 2 given conjugate positions A prime and A2 prime, which have a distance of 2 gamma. Suppose A is the position. This position and the projective lines point at infinity do not separate the conjugate pair. After some simple geometrical considerations, we conclude equation 30, where 2 gamma is the distance, A prime and A2 prime, and B equals V over C bigger than 1. Therefore, as the difference between distances of the observation positions O from the given points A prime and A2 prime is constant, it follows that the position of observation O registers on the plane a hyperbola having as focus points A prime and A2 prime. If we symbolize the major semi-axis with alpha and the minor one with beta, we have gamma squared equals alpha squared plus beta squared. The eccentricity epsilon is V over C. Based on the above, we will formulate the second fundamental theorem. The geometrical locus of the observation position from which a material point moving on the projective straight line E at supertubular speed, V, measured by Lask, appears to be simultaneously at the 2 given points A prime and A prime, is on the plane a hyperbola which has A prime and A2 prime as focus points and eccentricity V over C. As both the focus points and the eccentricity are known, the hyperbola is fully defined. Also, as the assumed plane is random, it follows, first corollary, this geometrical locus in 3D space is the hyperboloid surface generated by the rotation of the above hyperbola around its focal axis. Most interesting is the second corollary. The oblique angle formed by each of the hyperbola asymptotes with its focal axis equals angle omega. angle omega, which is formed by the boundary moving ray and of point A0 and the perpendicular, which ray corresponds to the Apollonian circumference, which is tangential to the projective straight line E. In other words, cosine omega equals C over V. Cosine omega equals C over V. This angle omega is the Cherenkov radiation angle to the direction of the particle motion, which superluminal motion is regarded as the cause of the phenomenon. This angle defines the region where the dark matter exists. Space void of any field. The above analysis produces a number of other interesting corollaries described in the book. Dynamics of the material point, the form of the unified field of light. Let's perform the following noetic approach. At the observer's position O, let's add a source of gravitational pull on the moving material point. Furthermore, let's assume that the material point, although constantly pulled towards O, is forced somehow to stay moving on the projective straight line E. We seek to establish the kind of gravitational force that is being exercised on the material point from the source at O. Suppose that now the material point moving with speed v measured by LASP, where v less than c, is found at position A. The observer now sees it at the conjugate position A prime in the Euclidean space, figure 12. According to the first fundamental hypothesis of this theory, the gravitational force and any other interaction between A and O comes from the conjugate position as shown in figure 12. Thus, this theory transforms a little the Newtonian gravity in the Euclidean space. In the projective space, of course, as both conjugate positions are acceptable, the interaction originates from both of them and is, in this case, much more complex. Here, very briefly, we shall demonstrate schematically the transformation of each form by choosing the one that originates from the nearest, time-wise, conjugate position relative to the current position, that is to say, the conjugate position we meet first if we were to travel from the position towards its past. Furthermore, in order to have the largest variety of directions, we choose the following. 1. The material point moves with superluminal speed, measured by us, and 2. Its trajectory is located as close to the gravitational source O that, from a certain position onwards, the interaction time is practically zero, Van Gogh limit, and the position coincides with its conjugate. This limit is arbitrarily defined by points AN and ANS on the trajectory. Points AN and ANS in the trajectory near the foot of the perpendicular P. The form of gravitational interaction when the material point approaches from the left is shown in figure 13. 1. When the material point is at position A1, the gravitational interaction corresponding to the conjugate position A1 2 prime, moving in the opposite direction is repulsive. 2. When the material point passes position A0, travels the interval A0 AM. A0 AM. Then it enters a space void, okay, thank you, void of any field. No conjugate exists. 3. When the material point travels the interval ans, there the position coincides with the conjugate position, so the gravitational is purely Newtonian, without deflection. 4. When the material point travels the segment ans, A0s, where A0s is the symmetrical of A0 in reference to P. Again, enters in the space void of any field, no gravitational. It's space void of any field. 5. When the material point travels the interval A0s AP, where AP has its conjugate, the foot of the perpendicular P, that is tan phi equals V over C. There, the gravitational interaction corresponding to conjugate position A0 prime is repulsive. Finally, 6. When the material point travels, moves away, and after position AB, for example, is in position A3, the gravitational interaction corresponding to conjugate position A3 prime, it's attractive. Summary. Adhering to Werner Heisenberg's philosophy, we introduced the localized observer as an absolutely necessary element of a consistent natural description of the cosmos. Furthermore, following the distinct separation of the geometrical from the perceptible space, and the choice of the projective space as our geometrical space, we formulate the first fundamental hypothesis of this theory, which is none other than special relativity theory's second hypothesis, properly modified. Thus, we established the theory of the harmonicity of the field of light, which attempts to explain a plethora of relativistic phenomena and attempts and observational data of the quantum world. Thank you all for your attention.
Okay, welcome.
If I understand this correct, you're saying that there's a repulsive gravitational effect at the near field level, in other words, close, as an element passes by? I'm not sure if I understood that, but that seemed to be the...
Repulsive.
Right.
We examine the case that the transformation is the gravitation is coming from the first conjugate position. We find first where we are moving in the past. So if we are moving in now, the point is at position A1. If we are moving to the past, the first position, conjugate position we find is A1, 2 prime. Because the projective straight line is closed. So we find first this. So this, the gravitational interaction corresponding to this conjugate position is repulsive. This is in superluminal speeds. we can find in some globular speech repulsive gravity. If we go to this, look, if the point is traveling here and it's in this position, the conjugate is in somewhere here. So the gravitational interaction corresponding to here is repulsive. Gravity.
Is that real, or is that, I mean, you're talking about conjugate points and so on, I mean, but is
This is my first hypothesis.
but do you consider that a real, or is that a fictitious thing that's based on the observations of perceptual versus?
I believe that it's real.
But no previous investigator has identified that before you. No previous investigator has identified that conjugate point as being important.
They don't find it, or he's asking.
Yeah, are you the first one?
I don't know. But this theory is 40 years. I work about this 40 years. I don't know if some other said that the interaction comes from the conjugate.
So what is the definition of observer?
Observer.
Yes. Is Schrodinger's cat an observer in the box or not?
No. Okay.
You were saying observer who can human being.
Do you remember? Heisenberg,
Yes.
the philosopher, and Weizsäcker said that we have physics, science. No, nature is first. But to have physics, science, you need the observer. You have no physics, science without observer. The observer is absolutely relevant of the science of physics.
But I think the cosmos keeps on going with or without the observer.
How do you know?
How do I not know?
No, how do you know? You need to be observant to show.